Good day, and welcome to CFE Media's Virtual Training Week for this session on how use of digital twins for predictive maintenance can transform operations. We'll be joined by Ralph Rio, a Vice President and Senior Analyst with ARC Advisory Group. I'm Kevin Parker, an editor with CFE Media and Technology. Following our presentation, be sure and stay tuned for a live Q&A on Zoom that will begin at 10:45 a.m. Central Time. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. This virtual class session is designed for technicians, engineers, and managers who want to better understand how the digital twin concept is being applied to predictive maintenance applications that can be used in industrial environments to improve productivity. We'll focus on the challenges and issues, technologies, infrastructure, and applications involved. You see before you the learning objectives for today's session. Here are some tips to help you get the most from today's webcast. Attendees are eligible for 1 PDH credit for this event airing on October 7th and is categorized within the technical, health, and safety categories, including core technical category or RECEP. This event is a live educational session presented on October 7th, 2020, and on demand thereafter. I'd now like to introduce today's speaker, Ralph Rio of ARC Advisory Group. Ralph has been with ARC since the year 2000 and is an industry analyst. He has been involved in many industrial domain areas and brings this knowledge base to his practice. During his 20 years at ARC, his research and well over 200 reports have covered digital twins, industrial IoT, enterprise asset management, and other concepts and systems relevant to digitalization. Ralph holds a bachelor's degree in mechanical engineering and a master's in management science from RPI, Troy, New York. Thanks, Ralph, for joining us for today's session. The floor is yours.
Kevin, thank you for that very nice introduction. We're here to talk about predictive maintenance. And predictive maintenance has been around for a very long time. But in the past, it was a very expensive custom application with a lot of technologies being chosen. And each time a preventative maintenance application was developed, a new set of technology would be used. This made them very difficult to support and maintain. So not only were they expensive to develop, but they often were very fragile too. As soon as something changed around them, they would break and people would go back to the old way of doing things. Now, the significant change is that new technologies that have lower development costs, much easier to develop the applications. They use a platform, so they're much more sustainable, and they last longer. And this has developed into a high growth area for the applications of predictive maintenance. This presentation, we're going to drill into the technologies for predictive maintenance, implementation strategy, benefits, and some conclusions. So just a little bit about the firm that I work for, ARC Advisory Group. Essentially, we're a think tank for industrial corporations, and most of our analysts have had operating experience. For example, I've ran a maintenance department early in my career, and we serve the industrial markets from the discrete manufacturing, hybrid manufacturing through the process industries, including utilities. Now, so I'm going to talk about my agendas, the digital transformation in maintenance, what are the benefits? And I'm going to go through all three of the major segments that use predictive maintenance. And then we'll get into business process and workflow to make sure the benefits are achieved. And if time permits, we'll go into a few case stories. Okay. Smartphones. You know, these were invented maybe 10, 11 years ago. And I have a list of items that, you know, I looked at the applications I have on my smartphone. I looked at the things that were replaced. And you see the picture on the right. That's not me, by the way. That guy's far more handsome. But it gives you an idea of the things that were replaced as a result of smartphones. And the software in them, the applications, general purpose device being able to replace a lot of hardware. And, you know, the point of the slide is that you are next. This is starting to impact maintenance, and predictive maintenance is the key application that is affecting that change. The software infrastructure used for smartphones has proven the economies of scale through consumer electronics have made it less expensive. And now this is moving into the maintenance domain. So I'll just describe that in a little bit more details. You know, we have a smartphone. Most of you probably have one in your pocket. It has I/O in it. Location is a key example. Your GPS coordinates. That information goes up to the cloud, and there are applications in there that do analytics on it, integrate it with other databases, and downlines the loads to your smartphone a map that tells you where you are in the world. Well, that technology can be applied to your equipment, like the mining equipment showed on the bottom slide there, and also units inside your plants. So there's sensors in these equipment. The readings are sent up to applications on the cloud. Some analytics occurred. An alert is sent to somebody who can do something about the problem. And the most common application happens to be predictive maintenance. And I'll get into the benefits later in the presentation. So at a high level, predictive maintenance today and the rapid adoption of it is leveraging software and infrastructure that was created via smartphones. Now, what's different between what we used to do in the past and today? So in the past, basically there was a manual processes using paper. Someone would print out a inspection work order. An inspector would get a stack of these papers, go out, look at the equipment, record data, come back. Someone would do data entry. In the process, hopefully they could read the technician's writing. There usually was a lot of data entry errors. So you had low quality as a result. And because it was a manual process and expensive, you had low data volume. So, you know, inspections and maintenance strategies were based on that were, quite frankly, relatively ineffective. With automated data collection, your data volume is high, and if there's something wrong, typically everything is wrong. So it's easy to identify the source of the problem and fix it. So very quickly, your data quality becomes very high. So with high data quality and high volume, that lends itself naturally to analytics, and those analytics can tell you when something's going wrong, which applies to predictive maintenance. And we see as a result of cloud and IoT, those technologies that were enabled by the smartphones we all have, predictive maintenance is a common growing application. So why do we want to do predictive maintenance? And this is kind of a short I'm going to go through this a lot more detail later on, but the key thing is to prevent unplanned downtime for critical assets. And typically a critical asset is one that when it breaks, there's unplanned downtime with it. There's lost revenue. There's losses of work in process materials. Usually there can be ramifications that are safety related, particularly in refineries, for example, where you're boiling oil, and there can be environmental impact. And this is just a quick summary in some applications where what are the losses? You know, it can be, in the case of the oil platform, $20 million per incident. In the case of a pharmaceutical batch, that's a bioreactor there. And if there's something goes wrong with that batch and they can't process it on time, the batch gets scrapped, and that can be worth $500,000 at times. And you see other examples in the slide. Preventing unplanned downtime is the key benefit of predictive maintenance applications. Another thing I want to emphasize here is the cascading effect. I present this because in this particular case, Duke Energy, they presented this slide and a lot of others during an ARC forum a few years ago. What happened is a transformer caught fire. And that fire cascaded in the other transformers, and then that cascaded into the turbines that generate the electricity, and turned into a massive amount of damage. In this case, it was $10 million. And that resulted in 4 months of downtime and the revenue that was lost due to that power generation. So, you know, it can go far beyond just a particular asset that you are supporting with predictive maintenance. So let's now bridge into maintenance strategies, and, you know, predictive maintenance being one of several maintenance strategies. So this is the common PF curve that chart that people refer to. One maintenance strategy is reactive, meaning you wait for the equipment to fail before you repair it. That obviously has some problems. Preventative maintenance has been an alternative. Now, this turns out to be fairly expensive because if you look at the recommendations that come out of the Nolan and Heap reliability study that they did back in the 70s, I think, and has become kind of the Bible for reliability. The PF, or the inspection interval, is 1/2 the PF interval. So when a problem is detectable by inspection, how long before that causes a process upset? Take half of that. That's how often you have to do the inspections. That is fairly expensive compared to predictive maintenance, where you're automatically monitoring the condition of the equipment that's generated an alert, and you then go do maintenance when it's really needed, rather than at these more rapid inspection intervals. And the benefit of the predictive maintenance is that you get much longer time to schedule the maintenance when the equipment is not normally operating. You know, that could be at another shift, or in case of some continuous process plants, when you take the plant down for an upgrade or scheduled maintenance, you can do the maintenance activity at that time. All right, I'm going to talk about the improvements later in the presentation in some detail. Now, this is key. You know, when I studied maintenance and reliability, I was trained for the bathtub curve, and that all assets have an early planned failure, and then there is this long period of time where the failure rate is really low, and then as this stuff wears, the rate of failures increase. And just to explain these curves, this axis, the y-axis, is the probability of failure, and the x-axis here is time. So as time goes on, as it wears, allegedly the probability of failure goes up. Well, these studies, United Airlines back in '68, Bromberg was a airline parts manufacturer in Germany, the U.S. Navy. By the way, these first two come out directly out of Nolan and Heap. There other reliabilities were done after that was published. The U.S. Navy is for ships that float, and then the U.S. Navy did another one for submarines. We see that on average, only 3% of assets have that bathtub curve that I was trained on and was told that all assets fail. That only applies to 3% of assets. If we look at all the assets that have an age-related failure pattern, it's only 18% of assets. Random failures occur for 82% of assets. So think about the preventative maintenance strategies that so many people do. That's only appropriate for 18% of assets because you want to do that inspection before the failure rate goes up. But if your asset has a random failure pattern, there's no uptick. So the likelihood is that a failure can occur between inspection intervals. And really, the inspections do you no good at all. So, this maturity curve model was published by ARC about 4 or 5 years ago. And since then, I've noticed that most suppliers and people who talk about maintenance strategy has adopted it. And just to go through it, as a result of your reliability analysis, some assets may have a reactive failure, maybe the appropriate strategy for it, where you just run the failure. Some other assets where preventative may be appropriate, that's those 18% of assets with an age-related failure pattern. And we do that for the engine oil in our car. Condition-based is where you essentially look at a single value, data value, and the example for your car is oil pressure or coolant temperature. And then predictive maintenance when it becomes multivariate typically, and that's battery management for your electric cars is how that happens. And prescription starts to give, in addition to doing predictive, starts to give the technician some guidance for how to do the repair. And we see that in the dealership level diagnostic equipment. And the way you get up above preventative is with IoT and analytics for the analysis to generate an alert when something starts to go bad. So the key point of this is that 82% of your assets really need one of these higher level analytics approach to asset management. And that the preventative maintenance that people so often talk about is really only appropriate for 18% of your assets. Now, as we start to talk about how you would implement predictive maintenance, we have to talk a little bit about the data because the data you acquire is obviously the foundation for doing analytics and predictive maintenance. And in general, there's talking about big data and small data a lot. And we hear a lot more about big data, where there is a large volume of data, a large variety of data. In this case, I'm showing things that could be PDFs as well as documentation about the assets and also the real-time data and historical data on the asset. And this is a lot of V, a lot of variability. So where that has been successful in the research that I've done is usually around executive KPIs and analytics to drill down and understand why those KPIs are going wrong and the offline analysis to go along with that. And some people use it basically to find data, where is that instruction manual for a particular pump? In a nutshell, it does not play well with predictive maintenance. What works well with predictive maintenance is a small data set. in the four S's: small, specific for a particular asset. It can be slow. If you think of a pump, the parameters change slowly over time. And the data for a pump is, in the example here, is structured. So we highly recommend that you do not take a big data approach. That is expensive, and it requires a lot of data science and a huge upfront investment for the big data. If you go to a small data set, and I'm talking about maybe 6 data values for a pump. With that smaller data set, you really don't need data science. It's well bounded, and the probability of success is a lot higher. So just to drill into this a little bit more detail, in this example for the pump, one could think about just 6 data values that would make for a very robust predictive maintenance algorithms. 3 of them are what I would call process data that would come from your control system, typically coming out of the historian. And 3 of them are additional data that probably would come through IoT. And I call it equipment data that normally is not in the process control system. Now, you can extend this to your medium data. If you have you do this for one pump, and let's say you have a process plant that has hundreds of pumps in it, you start applying it a broad based to your algorithm to a bunch of pumps, and now you can start thinking of the medium data of who's the best supplier and what's the best practice for maintaining that asset, or maybe applying it. Where is a half horsepower needed versus a 1 horsepower or 10 horsepower type of pump. Now, some of you are thinking for that equipment data that I mentioned. I go back a slide. This vibration, motor, current, that data that you would pull out of the equipment. Geez, do I have to throw out all my equipment and get new equipment with IoT access? I'll just point out, and the bold ones are common data, that for at least 2 decades, this equipment, PLCs, for example, robots, SCADA systems, CNCs, for at least 2 decades or more, these devices have had Ethernet ports on it that you could connect to and communicate with and pull out equipment data. So the odds are your installed base of equipment has a lot of pieces of equipment in it that you could communicate with directly. So now I'm just switching gears a little bit, talked about process data, equipment data. I'm just talking a little bit here now about the common path for implementation, all right? Now, typically the first step is to take data out of a historian, put it into an IoT platform. Usually that platform has very robust analytics. Most platforms that I've looked at have at least 12 or so or more analytics microservices for different types of analytics that you can do on that data. It can go from everything from SPC type things, clear up to machine learning or other types of artificial intelligence that go on to that data. So you get very robust analytics, and it's usually the interfaces have been made, particularly the IoT platforms that have been made for predictive maintenance and for use by control engineers or process engineers, those type of people. Hopefully a lot of people who are listening to this. A lot of it is the development has been simplified, so a lot of it is drag and drop. You drag in a data value into the analytics platform, and it starts doing analytics on that data value. And the output is something that you decide whether or not to do, generate alerts, all right? Now, as you start to need equipment data, as you decide to make that, if you get too many false positives, you will need to make the analytics more robust. So people start to add intelligent devices. This can be something like a direct connection to a robot or an existing PLC, or in case of older equipment, you may wrap something around it. You may take a PLC. I would recommend you use a PLC because it's ruggedized, but there are many other types of intelligent devices you can put on the plant floor. You wrap a PLC around it, connect the PLC to the existing I/O, in a parallel connection to the control system, and that's one way to add equipment data. If the sensor you want isn't available, what people do is add Wi-Fi. Or use existing Wi-Fi networks. A lot of plants nowadays have installed wireless infrastructure, and you can just use that. The wiring can be extremely expensive, and often just using Wi-Fi alone vastly reduce the cost of implementing adding the equipment data to your to make your analytics much more robust. And then you can also start thinking about adding other data sources like weather, stuff that's available on the web, or maybe data about humidity or facilities and stuff like that. So this is a common implementation plan. Start with a historian, intelligent devices, wireless I/O, and other sources like weather data. And you can make a very, very robust analytics with low false positives. Now, this here is just comparing two approaches. In the past, people would add I/O to the control system. Well, if you do that, because that I/O could potentially use part of control, you have to make that very, very robust. And it can cost $10,000 to add a point. People have told me that when you use something that is just purely monitoring, it gets a lot less expensive. You're not using it as part of the control system, so you can use wireless I/O. You can use less expensive sensors, and it's typically only $1,000 to add a point and to start doing analytics on it. And another key point is those of you who are reliability engineers can now get control of your own destiny because you can have a separate monitoring system. You don't have to beg the control engineers to add a point to their control system, which usually is problematic because they don't want to distract the control system from other things. Control should control the facility. You can have a separate monitoring system that you can then control your own destiny. Do predictive maintenance and alerts to prevent downtime. Now, just to go through the benefits for the manufacturer, first time fix rate. That should go down time because your predictive maintenance algorithm is giving you some sense of what the source of the problem is. For example, on a motor attached to a pump, if the issue is vibration, the odds are you should send out a mechanic out there. Maybe some bolts need to be tightened or a bearing needs to be replaced or something like that. So the odds are you send out a mechanic. If the problem is with current draw the electric motor, the odds are then you need to send an electrician out to evaluate what's going on there. So, just right off the bat, instead of, sending out somebody to do an inspection and then when you have a better understanding of the problem, send out the right skills, you can send out the right skills right to begin with. So because you have some idea what the problem is, the first time fix rate should go way down. Again, for the same reasons, the mean time to repair should go way down. And mean time before failure. Now, I'm defining a failure here as unplanned downtime, meaning that while production is using the piece of equipment, it breaks, it interrupts production, and you have a big business problem as a result. Your mean time before failure or unplanned downtime should go to near zero with a robust predictive maintenance program. And that has tremendous amount of business benefits about preventing lost revenues, idle labor, lost work in process materials. Now, let's convert those benefits that I just mentioned into business benefit that a senior executive would care about, including and particularly your chief financial officer. So we have a business benefit around uptime. If I convert that to, I can easily convert that to revenue, meaning that the equipment is running. While it's running, it's making product, and that product produces revenue. And if it goes down, and I'm talking about critical pieces of equipment, particularly ones that when they go down, they impact revenue, there's a clear business benefit there that the CFO and CEO would clearly identify with. The on-time shipment ones, if the equipment goes down, then production misses schedules. Often that results in missed shipments and customer satisfaction issue, which also in some industries can convert into a lost revenue problem because the customer goes to another supplier. Now, particularly in the discrete industries, this can convert into a WIP inventory reduction. One of the reasons you have work in process inventory between two pieces of equipment is that if the upstream piece of equipment goes down, you can use that work in process inventory to continue to run the downstream pieces of equipment. Well, if the upstream equipment doesn't go down when it's needed anymore, you have near zero unplanned downtime, you can reduce the WIP inventory. And that, of course, has a business benefit that falls into the balance sheet. With lower WIP inventory, that reduces or frees up cash, and it also reduces the inventory that's on the balance sheet. I'm going to combine this with asset longevity. With good predictive maintenance, your assets last longer, and that conserves cash, meaning you don't have to spend money to buy replacement assets. And oh, by the way, when you buy that new asset, it's carried on the balance sheet at a very high value because it's brand new until it's depreciated. So an older asset that's already depreciated, has a low value on the balance sheet, now has a much higher value. So the using of cash and the increase of assets, there are the financial analysts on Wall Street. They use those numbers to do financial calculations. And if the cash is conserved and the assets are lower, those calculations look a lot better, and the stock looks like it's much more valuable, and the stock value goes up. So by increasing asset longevity and by having less WIP inventory, that has a direct impact on the value of the stock, which obviously has a business benefit to the C-suite. I'm not going to go into the other ones. They're pretty obvious. I want to now convert those two into return on assets, a key benefit metric tracked in the C-suite and also by financial analysts. If you improve uptime, improve revenue, you have more profit. That's in the numerator. If you increase asset longevity and reduce WIP inventory, that reduces assets. That's in the denominator. And this is math that we all learned when we were in grammar school. This isn't complicated. By increasing the numerator and reducing the denominator, obviously both of those drive ROA up, which is a key benefit. And that's how you get executive interest and executive support for your predictive maintenance applications. And I highly recommend that you do not base your business case on reducing maintenance costs. I see that path is all too typically taken The C-suite doesn't usually care that much about that. It's not enough to get their attention, and it's then becomes difficult to get support for your predictive maintenance investments. If you instead take the approach of uptime, asset longevity, profit, and assets, it definitely gets executive suite attention, and it becomes much easier to get the resources you need to ensure success for your project. Those are the end user benefits. Let me talk about the benefits to an OEM for a moment. This takes a little different path. The OEM, we recommend the approach is to, these are for intelligent assets that already have a computer in them. That's when this works. Even if it's just an engine control module, which would be this particular case. Cummins took the approach that they first started taking data from the equipment. This is the first time development had access to real operating data from the field, and they used that to design a better product. This tested the infrastructure for data collection. Then the next step they took is they went to and they offered predictive maintenance services to their installed base. So the first part was to increase the market share for the products, to grow that revenue by designing better products. And the second step, the services, increase revenue by having a new product to offer their installed base. We find, by the way, that people who directly go to services, skip this step, usually muck it up, make mistakes, and really have to backtrack, and it delays the program for a year or two if they ever can get their sales force attention again. We highly recommend that if you're an OEM, you do the data collection first and then go to offering services. This obviously increases both revenue dramatically and gets executive attention. For you end users out there, we highly recommend that you add viable IoT strategy to your equipment selection criteria. Because if you choose a supplier that does not have a viable strategy, they are not going to be able to move up to this level. They're going to lose market share to somebody who does have a viable strategy, and their long-term business success is very suspect. Now, to put this in another way for you OEMs out there, this chart is your product life cycle chart. When you develop the product, you have a lot of sunk costs. When you sell the product, there is margin for the product. The area under the curve for margin is bigger than the area of the curve for development, so you have some profitability. When you add IoT and predictive maintenance services, the area on the curve for revenue and profitability goes way up. And it's reasonable to expect over time that eventually this green area could be 50% of the firm's revenue. Much higher revenue, much higher margin, a much higher valuable company from a stock viewpoint. And that gets executive attention pretty damn quick. For government, this may look a little trivial, but it's based on the engagements I've had with government entities, is real. And I'll spend a little time just talking about the uptime one. If when a resident goes to turn on their tap water and nothing comes out, or it's pretty ugly stuff, people get mad pretty quick. Or if they find out that when they flush their toilet, the stuff went out to ended up in a river or in a lake, they get pretty upset about that from an environmental impact viewpoint. So, uptime for water treatment becomes a critical factor to those voters. And you can say much the same thing about power. If you have a lot of power outages or power quality problems, you have a lot of residents that are unhappy, and people lose elections as a result of those kinds of issues. So PDM prevents those kinds of problems from happening, and your elected officials are much more likely to be reelected if there's good infrastructure. So let me just talk about business process automation for a while, for a few minutes. Alerts that get generated need to go to somebody who can do something about it. So, if an alert goes to somebody who's on vacation, or, the purchasing agent who doesn't have any idea what to do with it, or somebody who's really not involved in maintaining equipment, those alerts, lost alerts, result in unplanned downtime, which is what you were supposed to prevent. So your project looks like it was a failure. Our recommendation is that all those alerts go to somebody who's a maintenance planner. They can do triage, prioritize them, and generate work orders accordingly. We talked about process data and then adding equipment data so you have a more robust application. Again, those alerts need to go to somebody who can do something about them. That would be the planner. In case of a end user, for implants, that would be the inside a plant on site maintenance. That would be your EAM. And in case of an OEM who has a field service management application, that would be your field service management planner. They would go to work orders. We highly recommend you use a mobile device. And the reason for that is if you have paperwork orders, you have your data quality problem. And but if you have your mobile device, you can, as part of the data collection process, assure high data quality. And then your EAM and FFS system will become a trusted planning system. And just to talk about the mobile device, you can start adding business process automation to it. And I'd use, your ride sharing applications as an example. Somebody will type in, when they cross the line, they'll type in where they want to go. All right. But the application, your mobile device, already knows where they're coming from because the mobile device provides the GPS location. So you can think of those kinds of things that are in your mobile technician's mobile device to automate the business process. So, in this case, there's some analytics. It finds a driver that's in the area and asks the driver to accept it. The driver confirms, and the driver already knows where you are within 9 feet, knows where you want to go, and has a map to take them to that correct location. So you can see, and of course, there's a lot more business process automation that goes in after this when you want to pay for the drive, as an example. But think about this as you start using that mobile device. And just quickly, I'll go through a couple of case stories. One in particular that I like a lot is in this case, it was closing the doors. Number one, because it's simple. The IO that you need to know is how quickly the door closes. So it's simply when the door starts to close and when it finally does close. So it's 2 points and the time in between. And there's 6 doors on a train. So you develop the algorithm for one door and then replicate it for the 6 doors. And then in this case, I think there were 800 trains. So, you're covering 6 times 8 is a lot of doors. But with that was just one application development and huge benefits in terms of the trains running on time, because it turns out that the key reason a train doesn't run, and I think it was like in 50% of the cases, is because one of the doors doesn't close. This one I talked about, just mentioned before, unplanned downtime. The compressor is when oil is pumped out, crude is pumped out, it needs to be separated, the water separated from the oil. The first step is a compressor to do that. And in this particular case, it was a rather robust algorithm that a PhD developed and it was implemented, and it prevented unplanned downtime result. And as a result, that platform could produce more oil and prevented instances. This case has to do with power transmission. There's a huge installed base of transformers, tens of thousands of transformers that are part of power transmission. And this ABB offers a remote condition monitoring. They now do remote condition monitoring for over 1 million transformers. And this prevents unplanned downtime, like was experienced in one of my earlier slides. Here, Fisher Valves is offering a predictive maintenance for the valves, their valves, and they offer that as a value-added service. We're getting pretty close to the end of time, so I won't go into more detail about those case stories. I kind of ran through them quickly, but the conclusions you should draw is unplanned downtime is avoidable with good predictive maintenance. Predictive maintenance is now affordable compared to the old custom projects, and it's sustainable because of an IoT platform and the microservices. So the data management and the IT infrastructure that you use to implement this is maintained by the IoT platform, and you don't have to do this. And the key thing is, you reliability engineers out there, by using predictive maintenance and having a separate monitoring system separate from the control system, can have control of your own destiny. Thank you for listening to me. And now I think we're ready for the Q&A.
Well, thanks, Ralph, for a great presentation. We look forward to seeing you in a live Q&A session immediately following. Be sure and have your questions ready. Thanks for joining us, and we hope the information provided will suit your purposes.